Thanks for watching another TheCurioCat video. This is part 2 of our senior thesis project. If you haven't seen part 1, please check it out. In the last video, I only very briefly described what is the magnetic field strength H and the magnetic flux density B. So in this video, I would like to start by clarifying what is the H field and the B field. Here is a diagram of a magnet from the previous video. The green lines are called magnetic field lines. Outside of the magnet, the magnetic field lines extend from the north end of the magnet to the south end of the magnet. Inside the magnetic field lines extend from the south end of the magnet to the north end of the magnet, and then it continues in this loop. Now here I have written the definitions for H and B. H, the magnetic field strength, is a measure of the strength or intensity of the magnetic field at any point. B, the magnetic flux density, is like H in that it is also a measure of the strength or intensity of the magnetic field. However, B also takes into account the effect of the surrounding material, which can cause field lines to become concentrated. To better illustrate the concepts of H field and B field, I will draw some more magnetic field lines on the magnet. Now I will draw a blue oval to denote some enclosed surface. Actually, I drew two ovals. The first one I'll call surface 1, and the second one I'll call surface 2. How many magnetic field lines do you see going through surface 1 and 2? For surface 1, I count 10 field lines going through, which I colored in purple. For surface 2, I see 4 field lines going through, which I've also colored in purple. The consequence is that the more magnetic field lines you have going through a particular point in space, the stronger the magnetic field at that point in space. As a result, we can say that H1 is bigger than H2 and B1 is bigger than B2. Because remember, both H and B are measures of magnetic field strength. B and H is related through this formula, where the mu stands for magnetic permeability. Mu can be further broken down into mu r, which stands for relative magnetic permeability, and mu naught, which stands for the magnetic permeability of free space, which is just the magnetic permeability of a vacuum. Now imagine that we have an external H field, which is denoted by these green lines. Here I drew a blue box around some vacuum of space. On the right side, I drew another blue box, but instead of a vacuum, this blue box contains iron. Now you see, in the vacuum, the magnetic field lines are unbiased, or they're not altered when they go through the vacuum. But you see on this side, on the right side for the iron, the magnetic field line is biased in that the iron alters the direction of the magnetic field line so that they go through or are concentrated inside the piece of iron. As a consequence, on the left side, you have 1, 2, 3, 4 field lines going through the vacuum, while on the right side, you have 1, 2, 3, 4, 5, 6 field lines going through the piece of iron. Because the vacuum does not have a preference for soaking up the magnetic field lines, we say that its relative magnetic permeability is 1. But because the iron has the effect of soaking up the magnetic field lines, we say that its relative magnetic permeability is greater than 1. Thus, the magnetic flux density in the iron is greater than the magnetic flux density in the vacuum. So you see, given an external H field, the magnetic flux density B is a measure of how well a material sucks up the magnetic field lines. The more magnetic field lines a material sucks up, the more magnetized it becomes. This explains why iron sticks to a magnet. You see, the iron sucks up the magnetic field lines coming off the magnet, and so the iron becomes temporarily magnetized, thus allowing the iron to temporarily stick to the magnet. So essentially, the iron becomes a magnet, and magnets stick to other magnets. Here are the 5 equations that we've developed so far, and here are some notes regarding magnetic permeability, which we just discussed in the previous few slides. We almost have all the equations that we need to solve for the electric and magnetic fields in a wire. We just need one more equation. To find that last equation, we have to do a trick. Here is the big trick to solving Maxwell's equations. Let's invent a vector field A. We call this field the magnetic vector potential. It is a mathematical construct and has no physical meaning. Once we have invented this vector field A, there is a mathematical identity that states that the divergence of a curl of a vector field is 0. Okay, so what does that mean? It is actually very simple. Equation 6 tells you that if you have a curling vector field, then its divergence will be 0. An example of a curling vector field, which we have already seen, is the magnetic field H. Notice that it forms a closed loop in the form of a circle. However, it doesn't have to be a perfect circle in order to be considered a curling vector field. Here I have drawn two other vector fields that are also curling. Look at this rectangular vector field. It is still going into a closed loop, so it is considered a curling vector field. Same thing for this squiggly style field here. It is still forming a closed loop, so it is still a curling vector field. Equation 6 tells us that when we have a curling vector field, its divergence will be 0. That means if we insert an enclosed surface into the vector field, then the number of field lines going into the enclosed surface and the number of field lines leaving the enclosed surface should have a net of 0. To see if this is true, we just have to count the number of field lines going in and going out of our surface. Here, I see one field line going into the surface, which I denoted with a purple arrow, and I see one field line leaving the enclosed surface, which I denoted with a baby blue arrow. Therefore, the divergence is 0. As a second test, I have drawn a different enclosed surface. We will count the number of field lines going in and going out of the surface. I see two field lines in purple, one here and one here, going into the surface, and I see two field lines in baby blue over here and over here, leaving the surface. Therefore, the net again is 0. Now we have all 6 equations that we need to complete our project. Remember, A is just a vector field that we made up. It has no actual physical counterpart. In the next video, I will show you how we can use A to solve for the electric and magnetic fields. Okay, that's it for today. Thanks for sticking to the end. If these kinds of videos are useful to you, then please like, comment, and subscribe. If you have any questions or comments, please leave them in the comment section, and I'll try to get to them as quickly as I can. And thanks for watching.